Welcome to the course on FPGA based signal processing systems. We had been learning the finite state machines. As part of this finite state machines, we would be also doing different styles of finite state machines and then memory banks and also the timing controls of the Verilog in this week. As a first lecture in this week, that we will be doing this memory banks. So memory banks are used to store the data and retrieve the data as well. So if you want to suppose in the FPGAs we would like to generate sine wave. Okay, so the sine wave data, suppose per cycle, if we take a sine wave, this is t and the x of t, or this signal we need we sample it, and then number of samples per cycle suppose needs to be stored in a memory bank, and then suppose we take n equal to 128 samples per cycle. So for 50 hertz or 1 kilohertz, what about the frequency? Depends on that. The number of samples, are the sine values are calculated, and calculating them, after calculating them, these values are collected and these values are put in a memory bank, where memory bank has the location, that is, it looks like that. There is an address, okay, 0 1 2 3 4 5 6, so depends on the address. We can even extend the memory bank address, depends on the number of data we would like to store in. Okay, so this for n equal to 128, this should go from 0 to 127, and then the first sample value is fed over here, and then second sample, third sample, and so on. The width of this sample depends on the amplitude of this signal. Suppose that is going to be 2 volts or 5 volts. Okay, so how many bits needs to be accommodated for needed for the accommodation of this value. Okay, so here the width can be specified for the memory, that depends on the data value, and the depth of the memory can be decided based on the number of samples or the data which you would like to store. Okay, so here for example, it is taken from 0 to 15, that is 16 values. The depth is 16 values can be stored. Of the bit width can be decided based on the value here. So but here suppose we store this value, and then I would like to retrieve one by one sample, by choosing this address. Okay, so that is possible using the code, by storing this value and then retrieving it. That's what we are going to see in this lecture, that how the values are stored, how this memory is created in using Verilog, and how it can be in realizing in real time, how it can be stored and retrieved, the sine wave or the data, the sample data which you would like to store and retrieve. So the depth and width is here, as well as the chip enable. So you would like to have the suppose all 28 values, then you keep them, or you want to, instead of having one memory, we can have the separate, I mean this can be separated. For example, this is 0 to 15, and 4 memories of equal size can be made using this one, and we're going to see that example how this can be done instead of having a one memory. So either we can have one memory or multiple memories constituting the whole data as a one block. Okay, so this chip select is just to select the memory, which memory we are going to choose. So let's see that here. For example, here we have this, I'm giving the 0 0 0, and then this is given to be, for example, in this we considered 1 0 1 1 0 0 1 1 1 1 0 0 0, and then 1 0 0 1, then comes 1 0 1 0 1 0 1 1 1 1 0. So we have this combination 6 10 12, 14, 16 combinations. So if you look at this, this is A0 and this is A1 and A2 and A3. So we make that. So for A2 and A3 of 0, so you have the set of A0 and A1, which is 0, 0, 0, 1, 1, 0, 1, 1. Again, you can see the another set for this 0, 1 and A2, A3, 0, 1. Okay. So similarly, other set from 0, 0, 0, 1, 1, 0, 1, 1 for A2 and A3 as this 1, 0. Okay. So similarly here, using this property, and this is 1, 1. So for A0 and A1 is varying 0, 0, 0, 1, 1, 0, and A2 and A3 is constant for first 4 values, and then other next incremented ones for next 4 values, and then another one incremented of 1 for another 1 value, another 4 values, and then again it is incremented for the next 4 values. So using this here, we have separated this first 4 in one memory, and the next 4 in the other memory, and then third one in the next one, and the fourth one in this case. And so we have separated, instead of having one memory, we just have this 4 memories of smaller size, okay, which is having the depth 4, 0, 1, 2, 3, 4. And then the next 4 comes here, 4, 5, 6, 7. The location, you can see that how it is splitted, first 4 and the next 4, this is address bits, and then next 4, the third 4, and then this fourth one. So we have separated this as 4 bits. So having this M0, M1, M2, M3, and have this this is 0, 0, 0, 1, 0, 1, 0, 1, 1, which would be helpful to find out the address bit 2 bit wide A0 and A1. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. So this is the depth. So again this will be 0, 0, 0, 1, 1, 0, 1, 1, and 0, 0, 1, 0, so 0, 1, 1, 0, 1, 1, and similarly here. So here we have just have shown you here the width of this here also can be used to locate this memory, the other bits A2 and A3. So if this is A2 and A3 are 0, 0, then it is the first memory, and if this is 0, 1, that's going to be the second memory, and then 1, 0, 8 and A2, A3, that refers to the third memory, and 1, 1 refers to the fourth memory. So the one big memory is splitted into 4 in this case, and having the width can be, of course, depends on the data which we are going to store it. It can be a 4-bit or 8-bit data, or it can be a 16-bit data, and so on. So the data width can be decided as well. So this is used to locate the memory, and these last 2 bits to locate the memory here, and this two having the 0 memory, locate the memory means out of 4 which one, and this 0, 1 and 0, A0, 0 and A0, 1 decides this which location I mean of in one memory, and which location in another memory, and so on. So now we will see that 4 memories, and how in the Verilog code how we code it, and then how store the data, and then how we are going to retrieve the data. So from this, the module, we have the module memory bank. Okay, so the input is address of 4 bits. Okay, so we are going to use this in a 2-bit and 2-bit fashion. Also input chip select, which is going to select that if the memory, that is which memory, 1 or 1. Chip select, chip enable should be there for selecting that particular memory, and then having the output data which is going to be, again, this is a 4-bit here. So now declare these 4 separate memories. So what is this? Is the input output declaration for the memory, and then we have this input again. This is the address which locates the memory where we need to go in, where we are going to store the data or retrieve the data. And then reg, here you can notice this, declare 4 separate memories. In this case, the first we say M0, that is memory 0, You can see the reg declaration. Yes, it is going to be used or inside the always block. So we use that reg, but the square bracket with 0 3, it represents usually, so far we are defining this multi-bit vectors, right? Multi-bit, if memory is 0, 0 to 3 represents, if you put it in front of this 0 3, that means it is 4 bits. Okay, and here there is one more thing, which is square bracket 0 3. We have added this. This is something new, which says that this memory 0, yes, it is 4 bits. Here the width is 4 bits, but it has 4 values. It informs the depth of this memory. Okay, so it contains a memory 0, memory 1, memory 2, memory 3, that is index. This is the way to define the 2-dimensional vectors here. So and then memory 1, again, that's going to be 4 bit. Data is 4 bit. This can be anything, so 0 to 7 or 0 to 15, depends on the data width. And this memory 1 has 4, 0 to 3, again it has 4 locations. For memory 1 has 4 locations. So first 4 memory locations are decided over here. Next 4 is given to memory 1. Okay, depth, and then next is the 0 to 3, that is the width. Memory 2 has the next third 4 locations, that is the depth 0 to 3. So the next memory 3 has the width 0 to 3, and which has the depth again 0 to 3. So this represents the width of the data, and this represents the depth of the data. So each memory is M1, M2, M0, M1, M2, M3 are the 4 memories are declared over here. Now, so the temp is the variable which is used for the 2 bits. Okay, we'll see that into why this is declared as temp in this case. And initial begin. So initialize all this day. First store the values here. Okay, so we have to store the values. Our this memory can be for storing. First, let's see this how we are storing the values, like initial begin. Initial, you note down the initial here. We use it in the .v file, that is in the module. So usually this initial begin, we use it in the test benches, right? So this is a behavioral style of initial. When you say initial, it executes once, and memory 0 of 0 is given a data 5. Okay, so and then memory 0 of 1 is data 12, and memory is 0, and then it is 9. So we have this 4, the depth of this 4 values are declared over here. So that means initialized some value. So the data can be first 16 values of the sine wave. In that, we suppose we are going to store 0, 1, 2, 3, 4 values are stored over in the first 4 one. And second one, memory 1. So you can notice the difference between this 0 and 1 over here. And this is given some random data. It is not any sine wave or something. This is given a random data. So you can store the value which the data need to be stored. And memory 2 similarly, that is having another 4, 0, 1, 2, 3. Okay, so which is storing again these 15, 8, and 1 and 6. So the memory 3 again. So 16 values are stored in four different memories, of each having the depth of 4. Okay, so initial begin, then end. So initialize these values in the memory. So similarly, this size of the memory can be decided according to the data. If you want to store 128 data, then need to go for this splitting of memory, or if it is a split, if it could be split with this equal number of locations, that's fine. Otherwise, you have to use only one memory which can store all the values from 0 to 127, for example. So here I am showing the example wherein you can have the smaller memories as well. So this is now the values are in the data is loaded into the memory using this module, and then we'll assign this temp the wire which is declared as wire here, address 1 and address 0. So address 0 and 1. So if you see that 0 and 1, so here we have used it in this location. Sorry, 0 and 1 to locate this right, 0 0 and 1, which is giving the this one 0 0 0 1 1 0, and this is for chip select, or 2 and 3 are which memory it is going to be. So we declare that this is the first 2 bits of the address as temp. Okay, assign it. Now how we are going to retrieve this data which is stored in the memory? So assign data, chip enable is 1 for all the cases that when the chip enable, which chip has been chosen, chip enable, then it is going to be 1. If it is 1, then address 3, address 2. So address 3 and address 2, you can see this is 0 0. Okay, that refers to the address 3 and address 2 refers to the first memory or second memory or third memory. So if that is the case, look at the ternary operator, the data equal to chip select, and these 2 conditions are satisfied, that means these are 0 0, then memory 0 refers to the first memory temp, that is 0, the temp has this 0 and 1 address, in the 0 1 in the first memory, first location 0 1, what are the 0 1, what is stored over there, okay, 0 1 will be assigned to data. Else if any one of this condition fails, if it is not true, all of them, because it is an AND function here, so Boolean function. So this is, if it is not true, then assign this high impedance data 4-bit Z. Okay, so this is a continuous assignment. Okay, so and then next for this, similarly we vary this 0 0 0 1 1 0 and so on. Okay, so whatever the temp value, this if you keep changing this address, you can go for all the 4 values in using the test bench. So the temp can be whatever the value in the temp which can be assigned to data. So to retrieve the data from memory 1, then assign data, chip select is 1, and at 3 and 2, so 0 1. So you can see that this is referring to second memory, that is A3 and A2 bits. If this is true, then go to go for assigning this memory 1 of temp. Temp can vary from 0 0 0 1 0 1 1 0 1 1, that's 4 values. If you keep these conditions, then store this data over here, depends on the, otherwise colon here, it is 4-bit Z. So the next one, assign data referring to 1 0, this address 2 and address 3, memory 2 referring to third memory. If this is true, save this data over in the assign this to data, otherwise 4-bit here. Assign data, similarly chip select 1, address 3 and address 2 are 1 1. So all combinations of this 2 and 3. So memory 3 is located here, and the temp varies inside that memory 0 0 0 1 and 1 0 1 1. Saved to data, otherwise high impedance state. And so this is the test bench for retrieving the data from the memory. Okay, so this is using the assign statement. So let's see the test bench here, module, test bench module, and then inputs. We give this address, which address we were going to and see. So the chip select, wire 0 to 3, that data is 4 bits. Again, that integer we are going to increase it because we have this 16 data, and increase this index, use this for loop. So have the integer I, instantiate that module, dot address, chip select, and then dot data. Okay, so chip select or chip enable. Initial begin with initialize the inputs, address, and chip enable, and then end it. So initialize it here, and then go to the now how do we, what is the way in which we are going to retrieve the data for initial begin. So the display them, we as usual we use this display, that is the time and the address and the data. This is to monitor. For I is equal to 0, I less than 16, I equal to I plus 1. So this I need to be declared as integer, and this is the for loop which gives this address. We are changing the address through this for loop. I address equal to I. and give some time for each iteration. This is up to you, that hash 50 what is the, and n, this begin ends over here and this begin ends over here. So here keep changing the chip select. Okay, so chip select can be made one all the time, and then keep selecting that every data needs to be recovered, then you can use. Otherwise you can make on and off this chip select also. Sometimes the chip select is not available, and sometimes made it like a clock, but you can have this as a, it need not be on and off time equally. So it can be on for some time and then off for some time, or every time the chip select is on. So chip select equal to 1, then it keeps incrementing this I, and then I is saved to address. So the output we have here, see the this is I incrementing 0 to 15, and then here over this, and then we have this, because it is showing 32-bit, it is going over here, otherwise we will stop. So here is the data, this is assigned to address. So address is changing like this, address is changing, we'll look at it up to 15. So 0 1 2 3 4 5 6 7 8, and then address is changing. So address bits would be having 0 0 0, then 0 0 1, like that. So it's shown in decimal anyway, 0 0 1 0, and so on. So what happens here, if you see 0 1 0 0, in that case is when the chip select is 0. Okay, so chip select is 0, so the output, the one of the condition of assign statement is not fulfilled, so it is assigning this data is Z, that is high impedance state. When chip enable is 1, okay, yes, and then the address is 1, that is coming to be in the first memory 0 0, in the first memory, this refers to 0 0 the first memory, and 0 1 in that second location. What is the data? So that is 12, it is retrieving that 12. Again the chip select had made this at this point, it is not retrieving the data because this chip enable is made 0 over here, high impedance state. If you want to retrieve this data, make this chip enable 1 all the time, so that every data can be retrieved. So this is the 0 1 2 3, this is fourth data, which is 9. Okay, also this is the second memory, so this gets into the second memory, in this all these cases second memory 0 1 1 0 0 1 1 1. So up to this is going to be second memory, this is M0 and then M1. Second memory 4 locations, the data only 2 and 4 are retrieved here, that is 7 and 11. Other instances, this is the high impedance state because of the chip enable 0. Okay, then this comes with the 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1. So this is referring to the third memory, and again the chip enable gives the data at this location and this location as well. So the high impedance state in other two locations. Whereas here this is 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1. Okay, so up to this, so we have the data 10 and 2. Okay, so this is how to stop here. So with that, these are retrieved. So 10, 2, 8, 1 and 11, 7 all are retrieved. So if you make the chip enable 1 throughout, so every address change, the data can be, these Z's also can be whatever the data stored in this this first memory, and then 1 and 3, 1 and 3 of each memory locations can be retrieved as well. So this is reading the data, so storing them in the memory bank, and then how to read that or retrieve this data and then use it for some other process in the signal processing systems. So it gives these in the print, it gives these values just and the remaining you can see that it is high impedance also. Okay. So this is an example for how to create this memory banks with this assign statement. Anyway, it's a continuous statement. This same thing could be done with always statement as well. So let's see that Verilog module for the always statement module, which has this memory bank here input. So this address, chip enable, and the output data, as in the case of the same the reg data, which is 4 bits. Again, declare this 4 separate memories. We need to have reg 0, 1, memory 0, memory 1, and then memory 2, memory 3, and so all this 4 memory need to keep in mind. This is giving the depth of this, and this is giving the width of the memory. So wire temp. So now the initialize the values, whatever the values you needed. So that we have used the same data what is stored in this previous example as well, same data, and then 0, 1, 2, and 3. Now coming to the first, once initializing it, and we'll see the change in this code, like assign this temp. This would also be same, address 0, address 1, and then we are using this temp. That's why we are having the in the memory in the next one. So always we, instead of using this assign statement, you can go for this always also. When you use the always statement, it is this address or chip enable. So they begin the condition of that needs to be put in the if else statement here. So if chip enable is 1 and address 0, 0 and 0. So this is the first memory. If this is true, then assign this data, whatever memory 0 temp, it's equal to data. So the ternary operator is very simple, that it has in the assign continuous assign. Else the condition, you have this else condition is not given over here, you can see, and then that would be fulfilling. So this is like, this is a priority structure which would have else if, again we have this 0 and 1 condition, that is choosing the second memory, and memory 1 is stored in the data. So that is the temp which is storing the else if, the third memory again, that is 1, 0, let me put it 1, 0, and then take the memory 2, which is named, the third memory is memory 2, named as memory 2, and date assigned. Else if the condition, if condition 1, 1, and then date memory. So if this is not satisfied, else, okay, so then you have to have this else condition for this, okay, then 4-bit high impedance state. So both would work the same, but you need not write in this the fashion. This is the if else structure, okay. The other one, that is a assign ternary operator. So we'll in the synthesis process, we would learn what is the structure it will be realizing in that, whether it is if else statement or the conditional operator. If the conditional operator has mutually exclusive conditions, yes, it will go for this mux structure, okay. So the hardware with equivalent of this conditional operator will be mux structure. So if this condition is true, then go for this, else that. Here, if you use this if else statement, it will go for the priority structure. So priority structure will be realized in the synthesis process. So else data is this, so end. So we have made this if else statement using this always. Now you need to know them thing which is necessary is this data. So the data here we have how this data is declared in the module declaration. You can see this reg data 0 to 3, that is 4 bits data. This is required when you use it in the inside the always block. So the inside the always block, data is getting the values from memory, every memory. So this needs to be declared as reg outside the always block, that you can notice this in. So the test bench gets into memory bank TB, the same reg address and chip enable and the data, or that is 0 to 3, and then integer I instantiate this memory bank UUT, and then initial begin. We have this initialize the inputs, address 0 and address that's chip select 0, initialize them Then we have the display and monitor the usual time, address and data, how we are going to retrieve this. For loop, I equal to 0, I less than 16 and I plus 1. Integer, the I, this integer I, this which is incremented, can be stored to address I and hash 50 and n. So now the chip select, again we have made it like a clock. For sometimes it is 1 and then it is chip select is not enabled. So the output would be the same here in the case of memory bank which is retrieved. So first memory, that is M0, and then here next one M1, and then over here this is M2, and then 3 here, and this is M3. Okay, so we have this 4 each. Okay, so the data, you could see whenever the chip enable, the data could be retrieved and from the locations. This can be located, this is located, and you can see this is also same in all the other cases. So the high impedance state also, because this else condition gives the high impedance state in 1 and 3. So as I said that this could be retrieved using this data also could be retrieved using the chip enable 1. So the output at 50, so you can see here 50, this is 12, and then it's with respect to around here, that is 150, it is 9, 150 nanoseconds. Okay, so again 250 over here 7, and then 11, 1, 8, 10. Other conditions are 2, 2, 2, and high impedance state also can be seen printed. So the memory banks which can be created, instead of having this, we can have one memory of 0 to memory up to 15. That is possible to create a memory like this. So in that case, instead of 4 memory, so you will have this the command with this the bit is 0 to 3, the width of the data is this, but you can have a memory of 0 to this is 15 to 0. This is the command needs to be used. Instead of 4 memories, you can have only one memory, that is the reg declaration in the first, after this the declaration memory instantiations, and then initial begin assign this memory with 0, 1, 2, 3, 15. What are the, if you want to create only one single memory. So with this we have seen how to create a memory, how to retrieve this data from the memory, and we can also be using some from some file read mem be also a command which can be used to, from the suppose data is available in some files, and that could be read to the module to store it in the memory. So we will see them also in few lectures, how to read the file and how to open this file and then use that data in our module. Okay. Thank you.